All right, welcome back. So this is another requested video, so thank you for the request. And this is an ALEKS topic that's called calculating the pH at equivalence of a titration. There's really two different versions of this problem. Well, I guess really three different versions of this problem. Two of them are very similar, this one, and then when we have a weak acid being titrated with a strong base. But there's another version of this problem where I've got a strong base or a strong acid titrated with a strong acid or a strong base. So strong, 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 strong. And that version is pretty simple. And it will be, I'll go over it at the end of this video. So this problem will be the main focus, but at the end, we'll touch on that other type of problem really quickly. So if that's the one you're looking for, just skip ahead. Otherwise, stay tuned for this video. Okay, so getting started with this problem, the first thing I'm going to do is just sort of get oriented, take the words and sort of try to figure out what's going on. So I've drawn a little picture here, and these little pictures I find are a little silly, but I also think they're really useful and helpful to help us visualize what's going on. So I've got trimethylamine. That's going to be a weak base. That's going to be what I titrate with my nitric acid. So here I've got in my burette my nitric acid solution, little drip, 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 do my titration. And up here, I've started my balanced chemical reaction. And we always want to have our balanced chemical reactions to, ground us in what's going on. So this is my start. I recognize this as a weak base. And you might not recognize that as a weak base at this point in time. And that's okay. I think there's some hints or clues that suggest that it's a weak base. First and foremost, I know that this is going to be a nitrogen with a lone pair of electrons. That's a pretty common motif for a weak base. In the problem, we're told that it's being titrated with a strong acid, again, telling us essentially that it's a base, and the fact that it's not sodium hydroxide or potassium hydroxide or one of those other common strong bases is again telling us it's a weak base. The last piece of information is we're given a pKb for trimethylamine. That's telling you 100% that is a weak base. Anything that has a Kb is a weak base, and we're going to use that information a little bit later on. So weak base plus strong acid, then the product of that is going to be a protonated version of that weak base, a conjugate weak acid. And that's going to be very important as we move forward, plus NO3 minus, which is going to be the spectator ion. Now, this problem is asking us for the pH at the equivalence point. At the equivalence point is when the moles of weak base will equal the moles of strong acid, so all of this stuff will go away. So these chemical species, these are really going to be what's present at the equivalence point. So this CH3NH+, that weak acid, that's really going to be what we're ultimately finding the pH for, because that's what is present at the equivalence point. When I do this reaction here, these two species are going to neutralize one another, right? These two species are going to react with one another fully, giving us a weak acid and this NO3 spectator ion. So that weak acid there, that's going to be the thing that we need to take the pH of. So let's keep going. The first thing that I'm going to do now, right, I'm just now starting to get going with this problem, 6,323 molar. I'm going to recognize that I've got a volume and a molarity for my weak base. Anytime you see a volume and a molarity, the first thing I would do is just convert that into a number of moles. So that's my moles of CH3, which is going to equal the moles of HNO3. That's the definition of equivalence point. So I've converted this volume and molarity for my weak base to the number of moles, and then because I know it's a 1-to-1 ratio, at the equivalence point, I'm going to have the same number of moles of my strong acid. Now, I've been given the molarity of my strong acid, so with that information, I can now solve for the volume of strong acid that we're going to have to add. How much of this solution from my burette am I going to need to add, to get to the equivalence point? So that calculation will look like this, 0.1017 moles of HNO3 times 1 liter over 0.4990 moles. So here I'm just using that molarity as a conversion factor to convert from moles into liters. My units of moles will cancel. And this is going to tell me that 0.2027 liters of HNO3 solution will be needed to reach the equivalence point. So that volume of HNO3 solution to reach equivalence. So when you've added, another way to say that is when you've added this volume of HNO3, then you've added this number of moles, and when you've added this number of moles, you've reached the equivalence point because you've directly canceled out, essentially, your moles of weak base. Now, what we need to do is we need to correlate all of this information to what concentration of weak acid is going to be present at that equivalence point, because once we know that, then we can do our ice table. So CH3NH plus is going to be a weak acid, so it's going to dissociate like a weak acid does, and we're going to need that Ka for this weak acid. That's something that we can calculate using our pKb. We'll do that in just a minute. But first I want to talk about taking this information and figuring out what our initial concentration is going to be here for our ice table. We can probably fit it in right over here. So for my initial concentration of CH3NH plus initial, I'm going to need my moles divided by the total volume. Now the moles is pretty easy because it should be a 1-to-1 ratio. This is my moles of weak base. I'm going to react with the same number of moles of strong acid, 1-to-1-to-1. I should end up with this same number of moles. So the moles is going to be 0.1017 moles because all of this weak base has converted into this weak acid. And then my total volume, that's going to be this 0.2027 plus 160 milliliters, right? That's going to be the total volume that's inside of my flask here, and that equals 0.3627 liters. And so my initial concentration at the equivalence point is going to be 0.279 molar weak acid. So that's going to be what I put in here as my initial concentration. Now I'm just going to run this ice table. 0 and 0 minus x plus x plus x. Now we need to know what our Ka value is, right? So let's actually just finish jumping ahead a little bit here. Got excited. 0.279 minus x, x, and x. So now we need to know what our Ka value is in order to actually solve the rest of this ice table, right? To solve for x, we need to know what Ka is. So if I look back up here, if we're given a pKb, I can convert a pKb of 4.19 into a Kb. 6.46 times 10 to the minus fifth. The way I did that is just took this value, 10 to the minus power of this. That's how I get rid of the p. That means minus log, right? So if you were going to go to a Kb to a pKb, you take the minus log of this. So to get rid of it, 10 to the negative power of 4.19. Now, from my Kb, I can solve for a Ka for the conjugate weak acid, 1.55 times 10 to the minus 10th. And I can use that Ka down here, 1.55 times 10 to the minus 10th, in order to solve for my x value. 1.55 times 10 to the minus 10th equals x over x, or x times x over 0.279 minus x. I can solve this for x. This minus x term, that's going to be negligible. We can talk about that, but this value is so small. This, plus x minus x is going to be very, very small compared to that value. We can solve that for x. You could also solve it exactly, right? If you really like the quadratic formula, which I know that I do, so that's totally cool, times 10 to the minus sixth, and that equals my concentration of H+. So when you solve this x value, you solve this ice table, because it's Ka, then that x value is your concentration of H+, and you can solve for the pH directly from that, equals 5.18 for this problem. And that's it. So let's run back through it one more time just to make sure that we're clear on all of our different steps. Step 1, draw a little picture. I think that helps ground us. Step 2, write out a balanced chemical equation. Start thinking about what it means to be at the equivalence point. And then I figured out how many moles of weak base I had from the given information about volume and molarity. Anytime you see volume and molarity for something, you should think to yourself, oh, I can solve for the number of moles. Once I had that number of moles, I equated that to my moles of strong acid. At the equivalence point means 1-to-1. Then I found the volume of HNO3. That volume is going to be necessary to find my initial concentration at the equivalence point of my weak acid. So because I need my total volume, I need to figure out how many liters of HNO3 solution we're going to add. Then I can take my moles of weak acid, which is equal to my moles of weak base, right? That's where it came from this reaction, and figure out what my initial concentration of weak acid is. Then I run an ice table, got my Ka, which I figured out how to get up here. Solve for X, which is my concentration of H plus, pH 5.18. So this version and the weak base strong acid version are essentially the same, or excuse me, the weak acid strong base, the opposite version of this, are essentially the same. The steps are going to be the same, but there is a slightly different version of this problem that looks like this, where I've got a strong base and a strong acid. So in that case, the chemical reaction, sodium hydroxide plus HBr, is going to give us water, it's going to neutralize, plus Na plus Br minus. And Na plus and Br minus, they're not going to further react, they're not going to act as strong weak acids or weak bases, they're just going to be spectator ions. So this reaction is just going to give us a neutral pH. Anytime you have a strong base and a strong acid, you mix them together and you perfectly neutralize them at the equivalence point, you're going to end up with a pH equals 7, a neutral solution. So all of these versions, we can ignore, right, all of this information and just say, well, the pH should be 7 at the equivalence point when I mix a strong base and a strong acid. All right, hope that helps.